We continue now with the solution to the Schrodinger equation for the rigid rotor model. And I'll remind you, in picking this up, that we had left this off with this equation left to solve for theta. Now I'll remind you that we solved the part for phi and we got e to the im phi for that. And that involves setting the phi dependent part equal to minus m squared. So we have to set this part equal to m squared. Now if I multiply everything through by the function theta of theta and move the m squared over to the left hand side, I'll end up with an effective differential equation that looks like this. I'll have d theta sine theta d theta, sorry about all the thetas, plus beta sine squared theta minus m squared times the function equals 0. All right, now it may surprise you to know, but this is actually an equation that can be solved exactly. And the way one goes about doing it is by making a couple of critical substitutions. First of all, what we're going to do is we're going to let u equal to cosine theta. It's not necessarily obvious from looking at this as that's what you should do, but that's what works. And then we're going to make the association that this function theta of theta is going to be now written as p of u, and most of that's just so that I don't keep saying theta all the time. Now with this definition of u, we have the following limits on u. It must stay between minus 1 and 1 because it's equal to cosine theta. So that limits the range that this will be in. So when we apply these changes to this differential equation and do a little bit of algebra, but I'll spare you the algebra, we end up with a differential equation that looks like this. 1 minus u squared times the second derivative of p with respect to u minus 2u times the first derivative of p with respect to u. So now we've got an additional term in there. And then for this other stuff, it turns out it simplifies to m squared over 1 minus u squared, and then this is times p of u, and that's equal to 0. Now this is actually a well-known differential equation. It may not be one that you know, but it's one that's well known to mathematicians, and it has known solutions. And in particular, that solution can occur in two different phases. So I'm going to describe the two steps that one has to take in order to solve this differential equation. We're not actually going to go through in detail the solution, but I want to show you what the solution is and what it means. Okay, first of all, let's look at the case where m is equal to 0. So that means this term would disappear if m is equal to 0. Well, it turns out that when we do this, the solutions to the differential equation, and we would probably substitute a power series of some kind for p, but the solutions turn out to be a special form of function called a Legendre polynomial. Legendre was a French mathematician who studied this differential equation probably 200 years ago. All right, so these Legendre polynomials have the form p, and I'm going to give it a subscript L, and we'll talk about L in just a minute, and they're functions of u. Now the L, it turns out, is related to beta, and it turns out that the solutions under this case involve values of beta that must be equal to L times L plus 1, where L is equal to 0, 1, 2, and so forth, all of the positive, actually non-negative integers. All right, so these would be the solutions for this differential equation. These Legendre polynomials with beta equal to this value, with L being these integers, is the solution when m is equal to 0. What about when m is not equal to 0? Well, that clearly would cover a lot of ground too. So when m is not equal to 0, then it turns out the solutions are not the Legendre polynomials, but something called the associated Legendre polynomials. Okay, and these associated polynomials have a slightly different notation. They still have the L subscript, but now they have m up here because we've got to take account of the value of m and again they are still functions of u. Now you'll notice I've put the absolute value of m up here. What that tells us is that we're going to get the same polynomial whether m is plus 1 or minus 1, whether it's m is plus 2 or minus 2. Doesn't matter what the sign of m is, only the magnitude of m is what matters when defining these associated Legendre polynomials. Now the other thing that we know about these associated Legendre polynomials is that they can be calculated if we know the regular Legendre polynomials. And it looks something like this. If I want to know the Legendre polynomial for a particular value of m, what I would do is I would calculate 1 minus u squared raised to that magnitude of m over 2, so it's the square root of this thing raised to the magnitude of m, and then I've got to take the mth derivative. Now I keep putting m in absolute value signs because m can be negative, but you can't take a derivative of a negative power of a derivative, so that's why I'm keeping the absolute m's here. But if m were minus 2, then this would be a second derivative. All right, and it's a derivative of the regular Legendre polynomials. Okay, so this is basically giving us a formula for how we find the answers when m is not equal to 0. All right, so how would this work? Well, first of all, I should point out that this particular formula limits the possible values that m can be. Okay, because the p sub l's, it turns out, are polynomials of order L. Okay, so these are, let me write that down, polynomial of order L. So in other words, if L is equal to 2, then it's a second order polynomial. It's a quadratic polynomial. Well, if it's a quadratic polynomial, once I've taken a couple of derivatives, I can no longer take derivatives because I've got a constant there. So it limits the value of m. And in fact, what it limits the value of m to is that the magnitude of m must be less than or equal to L. It can't be greater than L because you can't take a third derivative of a second order polynomial. So now we have a constraint on the values of L, and it comes from this particular solution of this theta equation. Now, to show you how this works in practice, let's suppose I'll show you the first few Legendre polynomials. The zeroth Legendre polynomial is just 1. The first Legendre polynomial is just x, or u rather, and the third one is 1 half of 3u squared minus 1. All right, you'll notice that these are not unlike the Hermite polynomials that we saw when we were talking about the harmonic oscillator. All right, so what if I took this one, and remember this corresponds to m equals 0. So let's say I take this one and I want to find out what is the value when m is equal to 1. So it would be this particular associated Legendre polynomial. All right, well, I'd put it into this formula. I'd have 1 minus u raised to the 1 over 2, or 1/2 power. So that would be the square root of 1 minus u squared. I'd have the first derivative, because m is equal to 1, of the Legendre polynomial of this. Well, the first derivative is just 1. Okay, so in other words, the result would be the associated Legendre polynomial would be the square root of 1 minus u squared. Now, I've made the value u is equal to cosine, so if I substitute that back in, what I would ultimately find is that the associated Legendre polynomial, when I make u be cosine theta, is just sine theta. 1 minus cosine squared is sine squared. The square root gives us a sine. All right, for the associated Legendre polynomial with 0 up here, that's just the same as the regular Legendre polynomial. So it's just this. So that's just going to be equal to u. All right, where in this case, it would become cosine of theta. What about minus 1? Well, minus 1, remember when I stick minus 1s in here to these absolute value signs, I'm going to get the same thing back. So that's just equal to this Legendre polynomial. So once again, I would get this for p1 minus 1 of cosine theta. All right, so that gives you a little bit of a feel for how one might use this formula to find the solutions to this equation. Well, you know, once you build up from the earlier Legendre polynomials. Now I'm going to move on to the next page so that we can talk a little bit more about the energy eigenvalues. All right, so we've found from analyzing this equation that the values of beta must be equal to L times L plus 1, where L is equal to 0, 1, 2, 3, and so forth. Now, we also know from our substitution in the original differential equation that beta is equal to 2I times E over h bar squared. So now if I set this equal to L times L plus 1, what it means is that my energy levels, E sub L, are going to be h bar squared over 2I L times L plus 1. And these will be now the energy levels of our rigid rotor model system. Okay, now we might want to ask about the degeneracy. Well, we know for every value of L, so for each L, I'm going to have m is equal to 0, plus or minus 1, plus or minus 2, all the way up to plus or minus L. Okay, well, if I count these up, I got 2, 4, 6, 8, 10, plus 1. So in other words, I have a total of 2L plus 1 different solutions that correspond to this same eigenvalue right here. So that means I have a 2L plus 1 degeneracy for each of my eigenvalues for this rigid rotor model. Okay, this is something new. We saw some degeneracy in the three-dimensional particle in a box, but this is something new that we've seen for these other kinds of systems that we've been looking at. All right, so what we have here is a very sophisticated mathematical equation that gives us the solutions to these things, but as long as we're willing to accept that solution, we have actually a pretty clean result that comes out of this, namely this E sub L is equal to this set of energy levels. Now I should mention that the Legendre polynomials are in fact orthogonal to one another. So in other words, if I were to calculate, for example, the integral from -1 to 1, because that's the range of u in this case, and I did something like this sort of integral with p sub L of u, p sub L m, so let's make this k, a different value of u du, that when L is not equal to k, this is equal to 0. So in other words, they are orthogonal to one another. But they're only orthogonal if they have the same value of m here. That's an important caveat on this. So this is going to enable us to build in some orthogonality to the solution to the rigid rotor eigenstates, eigenfunctions. And remember that those eigenfunctions now can be written because we originally had psi as our total eigenfunctions. That was equal to a product of our theta-dependent eigenfunctions and our phi-dependent eigenfunctions. And so we're going to end up with something that looks like a normalization constant times our associated Legendre polynomial with cosine theta as the argument, and our phi function over here. And so these are the functions that we're going to explore as we talk about the eigenfunctions of the rigid rotor.